So p-values are random, uniform, or beta, oh no, sorry, not 0, 0, 1, 1. You remember the beta distribution? Yeah, so it's p to the alpha minus 1, 1 minus p to the beta minus 1. So if alpha equals beta equals 1, we've got a uniform distribution because you've got no relationship here. Okay. Danger, looking at many p-values and picking the smallest. Just as I've done there. You look at a whole bunch of p-values, you find the smallest, and then say it's significant. Well, one of them's going to be the smallest. How can we think about this? Well, I'll show you two ways to think about it.
So would you just roll with the overall p-value?
Yes, well, the question was, you roll with the overall p-value. Yes, but I will give you another tool as well. So yes, the first, lesson number 1, that is the overall p-value for the overall data set. Okay? What I'm doing is trying to teach you how to view these separate p-values individually. So R unif 10, that's the same as the random numbers from a uniform distribution. There they are. If I do it again, they're different, of course. So these 10 are the same as these 10, just the same, notionally anyway. So I'm going to find the minimum of those. Oh, look, it's significant. Straight away, I've committed a type 1 error. Remember, normally I stand here like an idiot, typing away, going return, 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 and I'll say eventually, one time in 25% of the time, I'm going to make a type 1 error. And then when it happens, I say, look, but I had to wait a long time like an idiot for this to happen, so you presume that that is rare. How long did I have to wait until I made a type 1 error here? First time. Let's try it again. Again. Oh, I got away with it that time. But you can tell it's more common than it was. Let's there's 100 of them. And you can see just by looking at it that not all of them, but quite a few of them are less than 5%. So let's ask whether they're less than 0.05. Some are, some aren't, of course, and we'll make a table. So how often do you reject the null hypothesis for one of those tests? Half the time. So your type 1 errors are a lot more prevalent if you just uncritically look at all your p-values and find the smallest one. Of course, for a single one, it's going to be less than 0.05, only 5% of the time. But because we've got multiple, you've got the coconut standing there and you're throwing your ball at it again and again and again and again, yes, of course, it's going to be less than 0.05 quite commonly. And of course, if I've got more than 10 here, make it 20, what's going to happen now? Just as a guess.
It's going to be up about, up about 70.
There you go, 64. And the more I try, the more I do, the more chance I've got of committing a type 1 error. It's a pernicious and difficult to deal with problem. Let me go back to my original data set with D. We'll have another look at it, if I can find it. Suddenly, when you look at that p-value, it's not so significant, is it? what you've done is found that there's nothing special about this one. This smallest one could be anywhere and you'd say the same. And the analysis I've just done with a minimum of 10 p-values, all I'm doing is looking at the smallest. And all we were doing here was looking at the smallest. So we need some way of correcting for that. When conduct on the same data set doing that means when you conduct multiple tests on that and declaring that at, this induces, no, actually not induces, it inflates this one. Okay. So the way around this I say the way around it. I'll explain that later. The way around this is to use a thing called a Bonferroni correction. Bonferroni correction.
It's like there's a lot of Italians in statistics, or everything seems to be named after.
Bonferroni?
Wait, Bonferroni sounds Italian to me.
Bonferroni is, well, with the I at the
Berlusconi
end of it.
sounds Italian to me.
Yeah. He got Poisson, he was French.
Berlusconi, I don't think he's a famous statistician.
Berlusconi, no.
Philanderer.
Well, I mean, we had another thing in here that was.
Yeah, Bernoulli.
Bernoulli, yes. Yeah, Bernoulli, fair point.
Yeah, but you think about it, it's like, where did our culture come from? We came from that European base, so therefore we're only like 200 years old.
Oh yeah, I know. I'm
And
just saying.
they've had.
Speak for yourself, 32.
Well, our New Zealand culture is just here. That is like 2,000 plus. So they've had 2,000 years more of experience of being able to come up with things like this. So.
True. But then a lot of our mathematics come out of we've only
had about 400 years. It was all religion before that.
Yeah.
Bonferroni correction. You take the p-value and multiply it by the number of tests conducted. My writing's going. Conducted. Which in this case is 10. I think, or is it 11? Have I got? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, so p equals 0.0291 goes to p equals 0.0291 times 10. Not significant. It's a confusing and difficult issue, and I would like to say that if you think about it deeply, you will get the right answer and think about it in the way that I do. But unfortunately, it is a difficult issue, and I'll tell you why. If we had this data set here, and before I looked, you remember the prior and the posterior that we looked at in Bayesian analysis, right? So your prior is what happens before you look at the data. You look at the data, you update your beliefs to a posterior. In the prior world, I haven't seen that data set. If somebody came up to me and said, I think type C is a lot bigger than type A, I would say, let's have a look. and I'll do the test and other ones as well, it's significantly bigger. Because somebody came up to me a priori and said, I want you to look at type C. Do a test. And I don't want no trouble, so I do a test, and I get a p-value and it's significant. I say, there you go. Compare that to the other way of looking at it, which is we've got 10 different types. I'm going to do an overall test. I'm going to write the p-values down, and I'm going to see what I find. Do you see the difference between those two? In the second way, we've got a whole bunch of random p-values, and we've looked at the smallest. There's a fine line between those two, and sometimes it's not clear where you are. If you do this kind of analysis, I want you to justify it. So the Bonferroni correction, basically multiply by 10. This is a very conservative. Correction. There are others. But these are complicated. The Bonferroni correction is by far the most frequent. I think I'm spelling it right. Bonferroni correction. Bonferroni's correction.
So the Bonferroni is just helps you correct for that
That's all it is.
one thing.
It's because you're doing blunderbuss
Bring it in
statistics.
line with-
You just bring it in line with what p-value actually means. You're just correcting for the fact that you've just identified the smallest of 10, or smallest of however many. Sorry.
If you've got a large number of p-values,
Yep.
say 100, would you use a different thing other than Bonferroni? Because it would be very difficult to have any p-value times 100 that would reach a level
No,
of
it would work fine. The question was, what would happen if you had 100 or 1,000,000 tests, yeah?
Yeah.
Well, let's just say n equals 100. What do you need? What do you need a p-value to be out of 100? Let's try that. Let's turn it round. Let's say for the 0.05 level, you need a raw p-value less than 0.05 over 100. Yeah? So if your p-value, if your smallest p-value out of 100 is 0.0005, when you correct it with the Bonferroni correction by multiplying by 100, you're still below 0.05. But see, with a large number of tests, you need a teeny tiny p-value. Yeah?
How do you, if you have 1,000,000 tests
Yep.
and you want to find the smallest one,
Yeah.
you're not going to go looking through 1,000,000 pages of numbers to find it. How do you pull it up? Mid.
Oh. Ah. The question was, how do I pull up all the p-values?
Or just the one that you want. Without having to search through all that.
There is a way, and I'm struggling to... oh, here it is. Are these them? Oh, I don't know. I'll get back to you on that one. Yes, you can do it. Yes, you can. R will do this for you. It will search through them all and give you a list of the p-values, but I'm getting myself flustered and tangled up. The Bonferroni correction. Yeah, if you've got totally random data and you do the same test on it a bazillion times, you will get significance because there's crud everywhere. It's only a certain colour that causes it. What's your null? No, the null is that no colour causes it. Nothing causes it. You know is that jelly beans do not cause acne. Now we've got a second feature here, which is the colour of the jelly beans. All right? What's going on? We found no link. We found P is greater than 0.05. You see, I'm not just making these things up. This is from the net, you know. This is not me. We found no link. No link. Is there an exception anywhere?
Yep. Second from the right.
What does he say? Whoa! Do you see what's going on here? It's just the same, isn't it? What colour was it? You see, all these are different ones. Salmon, red, turquoise, magenta, yellow, blah, 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 green. All right? And they're absolutely correct. What should they have done? Apply the Bonferroni correction. And then you got, what, 30 or 40 colours? So whatever the p-value was, it's possible to get a result. Possible to get a significant result, but you need a p equals 0.0000, whatever it would be, because after you multiply it by the 40, it's still got to be less than 0.05.
In a sense, their first test, the very first test said no jelly beans. So why would you even continue on?
The question
There's
was,
no link
the
between
question
jelly
was that this first test should mean that you stop.
Yeah.
But maybe
Just maybe.
the red ones give you acne, and because they're only present in a small proportion of your jelly beans, the red ones cause acne, but you can't detect that
I
because they're only rare.
Okay, I would have thought that if you found there was a cause, and then you say, okay, which ones then probably cause?
Yes, possibly. There's a whole bunch of stuff on serial tests which I could go into,
Would
but
you just test the food coloring rather than the other thing?
I guess that's what they're doing. Yes, they are just testing the food colouring rather than the beans themselves. But I like this. XKCD is a very profound cartoon. Sorry.
And do you still apply the Bonferroni even if the overall, the first NO was significant? Do you
Ooh.
still then apply the Bonferroni, or is there another one that's slightly less difficult to find significance?
That's a good question. The question was, if the first p-value was significant, the overall p-value is significant, I don't know the answer to that. The reason it's difficult is that the Bonferroni correction basically assumes independence of the p-values and also implicitly assumes that the null is true. That's why it works, because all of this stuff is controlling type 1 errors, which is predicated on the null being true, of course, because you're looking at rejecting it when it's true. If it's not true, all bets are off. And I don't have a good answer to that. That's an excellent question, but I don't know the answer. I'll have to think about it. There's what?
Tukis or something. There's other types of second order tests.
Oh, there's a whole bunch of stuff you can use. Yeah, there's Tukis methods as well. I'm going to stop there and have a little break. I want you to think about this in relationship to your own portfolios, because you've all got data and you're all applying lots of tests separately to it. So just be aware of the Bonferroni correction. I'm not going to come down hard on people who have applied it slightly incorrectly, but you need to be aware of it and you need to tell me that you've been using this in your thinking. Okay, I'm going to stop for about 5 or 10 minutes and then we'll get going again. And I'll get an answer to your question as well.